This is module number 15, can you believe it? We're looking at equilibrium again with Le Chatelier's principle and how that shifts the equilibrium, okay? So this lesson's a little bit less than last module, so hopefully you spend a good amount of time on module number 14 and kind of understand what's happening with the shifts in equilibrium. And so this is a little lab activity that we would have done, so we can just do a sort of a dry lab on page 9 and 10, and then page number 11 is just an example homework question where again, the chemicals are too toxic that we wouldn't have done that in the lab anyway, so it gives you a chance to practice. Don't forget, we're always explaining what's happening at the molecular level, okay? So the definition again, Le Chatelier's principle, when a stress is placed on an equilibrium, the equilibrium will shift to reduce that stress and a new equilibrium is established. So that definition is when you want to think about with all those sort of 3 or 4 key points there. You'd be looking for those. I'd be looking for those to sort of check them off. Okay, so think about the wording, and we're going to watch a little bit of the Bozeman science clip now, because again, it shows a nice little animation there with the example from the Haber process. Haber, tomato, same sort of thing. He calls it the Haber process, and the video from last module says Haber process. It doesn't really matter, but you can see the animation in this little clip that we're going to watch. So we're going to watch just 2 minutes of the Bozeman science, and then you can watch the rest of this video because I'll link it to the classroom. Okay?
Principle, also referred to as equilibrium law, and it's a really elegant principle that you apply to reversible reactions. And it basically says if there's ever a disturbance to equilibrium, the reaction will move to counteract that disturbance. And so let's say, for example, I'm at an equilibrium state between reactants and products, and I all of a sudden get an influx of reactants, way more reactants. It's going to throw my equilibrium out. And so what can I do? Well, since this is a reversible reaction, I can move the reaction from the left to the right according to Le Chatelier's principle. And as I do that, I increase the amount of products and I bring it back into balance. That's essentially Le Chatelier's principle. And so according to that, in any reversible reaction where we have reactants and products and it's established in equilibrium, if we ever have a disturbance, and that disturbance could be adding or removing chemicals, it could be a decrease in volume, an increase in pressure, it could be an increase in temperature, a decrease in temperature, or even dilution, what's going to happen is a new equilibrium is going to be reestablished again. And so let me give you an example of that, a graphical example. If we're looking at the Haber process where we're taking nitrogen and hydrogen gas and converting it into ammonia, this could be our initial equilibrium, where we have given amounts of concentration of each of these. But let's say at this point right here, there's an influx of hydrogen. So we're increasing the amount of hydrogen. So that means we're increasing the reactants on the left side of the reaction. According to Le Chatelier's principle, the reaction simply moves to counteract that additional reactants. And so which way is it going to move? It's going to move to the right. And so what's going to happen to the amount of hydrogen? It's going to decrease. What's going to happen to the amount of ammonia? It's going to increase. What's going to happen to the amount of nitrogen? It's going to decrease because it's a reactant as well. And so a new equilibrium is going to be established. And so if we look at this at the molecular level, so this is all of our gases. Again, they're all mixed in together, but we have varying amounts of that. Let's say we get an increase in the amount of hydrogen gas. How can we get rid of that hydrogen gas? We can simply combine it with nitrogen, make more ammonia, and then we can reestablish that new equilibrium.
Okay, I just want to take it back for 1 second here and just pause it. You can see right here that there's a calculation we're going to be doing. That's the next module, okay? So we're going to start to think about now, can we figure out if this is a system that is at equilibrium or not? And we're going to be doing some calculations, okay? So get ready for that for the next module. So for here, we've got an example. We're going to consider this equation. And if we had an equation with nitrogen, monoxide, and oxygen gas, there's your equilibrium. And so you can see what would happen if we had an addition of oxygen gas. Again, that increase in concentration of oxygen is an increase in concentration of a reactant. That's my stress. It's going to shift it to the right to be able to produce more product. And you can read through here, but basically, we're always explaining things at the molecular level. Well, here you go. What happens at the molecular level? You're going to have more collisions between the molecules. You're going to have more successful collisions between the molecules. And so you're going to end up with more product. Okay? Remember again that we always think about the reactants as things that are on the left-hand side and the products as things that are on the right-hand side. So even though we talk about the reverse reaction and then the products are really the reactants, don't worry about ever changing that up. We always just consider what's on the left as the reactants and then our equilibrium symbol, and then what we have on the right as our products. So we'll always talk about it in terms of the forward reaction and then the reverse reaction. Okay, and yeah, of course, when you do the reverse reaction, the products are now really the reactants because they're doing the reacting together. Okay, don't get yourself hung up with that. But remember, the terminology is going to be quite important. So here we go. If our example says, what if we increase the chlorine gas concentration? Chlorine gas in this example is over here on the product side. So my stress is an increase in concentration of my chlorine gas. What's going to happen? That's my shift. My shift is going to be to the left. It's going to be towards the reactants. It's going to favor the reactants. There's a whole bunch of terminology that we use to explain the same thing. You can use any of them, okay? But it all means the same thing. It's going to shift to the left. When you shift it to the left, which is going this way, what is the result going to be? You're going to have a decreased concentration of chlorine gas, a decreased concentration of, remember that, decreased concentration of the chlorine gas, increased concentration of the oxygen gas, increased concentration of the hydrochloric acid because of the shift towards the reactants. In terms of collision theory, can you explain that? Yep. 1, frequency of collisions between the water and the chlorine are going to increase because you have more particles because of that increased concentration. 2, increase the likelihood that these collisions are going to occur with the correct collision geometry. With energy that's greater than or equal to the energy of activation, you're going to increase the rate of the reverse reaction. Okay, and therefore, as the chlorine gas concentration decreases, you decrease the rate of the reaction of the reverse direction, and as the concentration of the oxygen increases, you're increasing the rate of the forward, and that's going to occur until you reach that equilibrium state. And at equilibrium, the rate of the forward direction is equal to the rate of the reverse direction, and that's the terminology. That explains how a new equilibrium has been established. Okay, so kind of got all those points there. That's your nice summary right here. So here we go. Let's do an example that we would have done in the lab. Okay, so here we have some iron 3 nitrate being dissociated into iron 3 plus and 3 nitrogens. Your iron gives you the yellow-orange color. Okay, and we haven't used an equilibrium sign here because simply we're just not at a saturated solution. And it's still being dissociated until you get to that saturation point. Then we would put an equilibrium symbol in. We'll talk about that later when we start talking about salts and dissolving. Okay, so you've got some colors established here with these ions. Take it to the next page. And now, what happens when you pour these 2 test tubes together? So we would have done this in the lab. I'm going to post a video that shows you what that looks like, okay? So you can see this example essentially together. What do we have? We have our yellow-orange colorless on our reactant side. We've got our nice equilibrium symbol here, and then that blood red, really blood red color you're going to get with that product, okay? So now we've got an equilibrium established. Let's try to stress that equilibrium. So first step number 1, if you add some distilled water, what's going to happen? You just get a lighter blood red color. You're just diluting it a little bit. That's not our equilibrium yet. Test tube number 2. What if you add 10 drops of a 0.2 mole per liter solution of iron nitrate? Okay, so here we go. Let's use our terminology. What is happening? If you're increasing the iron 3 concentration, okay, your iron 3 concentration is over here. I'll make a little bit of a mess on this sheet and I'll tidy it up when I post it. It's going to shift to the right. So that would have been your prediction, right? And what would it look like? So at that new equilibrium that gets established, you're going to have more of the product. And so it's going to be darker red. And you can see that. All right, let's do the second one. So for test tube number 3, what if we added 10 drops of the KSCN? So what are we adding in? We are stressing it by adding an increase in the concentration of our SCN. And if you increase the concentration on a reactant, it's going to shift it to the right. And what would you see? Darker red color. Let's do the next one. What if you're increasing your Fe2SO43? So what are we doing here? This is one of those two-part questions, okay? You need to recognize that if this is aqueous, that means in a solution, you have some of these ions present, and you have some of these ions present. And are any of those ions in my equilibrium expression? Yes, they are. That is translating to our Fe3+. So that's my stress. What would be your prediction? Shift to the right. What would you see? Darker red color when a new equilibrium is established. Okay, next one. What if we added some NaOH? All right, here we need to know that if you have all of these ions available, what makes a precipitate? Well, if you're adding sodium hydroxide, you've got sodium ions and you've got yourself some hydroxide ions. So now you need to know that that's going to actually make a precipitate. What does that mean? That's going to mean that once you add the sodium hydroxide, the hydroxide is going to bond with our iron ions, create a precipitate. What's going to happen to the concentration of the iron? It's going to decrease. That's my stress. Decrease in my Fe3+. I predict then if it's a decrease, it's going to shift which way? Yeah. Remember when we did the summary table in the last module and I said, memorize the increase. And then by default, the decrease is the opposite one. Of course, it makes sense if you think about it, but it just makes for less things to have to think about because if you memorize, right, I got an increase in the iron, it's going to shift to the right. Therefore, if I decrease the iron, it's going to shift to the left. Less molecules, less collisions, it's going to shift to establish that new equilibrium balance, right? And so if this case, you shift to the left and you have less of the iron there, you're going to have less of the FeSCN because you're going to be making more of the reactants, right, to compensate for that. So is it going to go darker red or lighter red? It's going to end up being lighter. Okay, stop for a second and see if that makes sense to you, yeah? Okay, next one. I've already done a little bit of work for you here. Here we go. What if you added some silver nitrate? Okay, silver is going to bond with the SCN ions. And where are the SCN ions? Well, they're right there on the reactant side as well. So my stress is a decrease in my SCN ions. It's going to shift to the left, and you're going to get a lighter red color. Next one. I'm going to let you work through these ones and see if that makes sense to you, okay? Can we explain that? Yeah. And here's a good explanation for what happened with step number 5. Stress, decrease in your Fe3+ concentration. What's the shift? To the left. What's the result? Increase in SCN ions, decrease in the FeSCN2+. At equilibrium, it's going to be a lighter yellow color. So you see how you can sort of summarize that in one sentence or with all those 3 little points there? You would do the same for step number 6. Okay, and I've already written that one in for you. And I'll leave this one for you to do on page number 11. I'll just get you started here. Okay, this is really the homework question. So again, it's not too long for the module if you get what's going on. You can watch the YouTube video that it links there, and I'll post that as well. Just again, this is a toxic one, so we wouldn't do this in the lab anyway. Write your colors underneath, and then you can see what would happen, and then fill in the table. But don't look at the solutions until you actually give it a try on your own. Okay, sound good? That's it for Le Chatelier's principle. Good luck with that. I hope it's not too tricky. Okay.